Cece? Am I pronouncing it?
See,
Cece? Okay. It's a lot easier than I made it. All right. Let's see. Give me a second. Try to guess. Student? Last name is no. All right. All right. Some multiple choice test here. Yeah. Whitaker. Yeah. All right. So I had the first name correct. I don't know what said Newton, because you share the same first name as that person.
what's that movie here?
Huh?
Isn't that a movie?
Yep. Morning. Mark, right? Yeah. All right. Matthew.
Sir.
Got less than a minute left. Yeah, 8 o'clock. We'll get started. All right, for those of you online, make sure you email me after we're done. Send in the email, include the keywords. So the first keyword for attendance will be keys, like Florida Keys or things in my pockets. So really quickly, before we jump into chapter 2, I'll give you some announcements and reminders. If you had lab last week, if you were in lab last week, you don't have to come to lab this week. Remind you, redoing the first lab, people who couldn't make it. Because it was the first week, so just trying to be a little bit flexible. So if you're not here on Wednesday for the lab, just be here Wednesday, this Wednesday. Make sense? All right, for those of you who were here on Wednesday, again, you don't have lab, but your lab that you did do is due Friday. So not last Friday, but this coming Friday. And of course, obviously, it's not normally like that. Usually it's due the Friday after your lab, but in this case, it's extenuating circumstances. Also, because of this change we're making, if you look at the schedule in the syllabus, it says that there's no lab on the week of Labor Day. Again, as a reminder, now there will be. Any questions about the lab? All right. The other announcement is between my stepdaughter and my sister coming into town, I've essentially got no work done. So that's actually good news for you. So first of all, yeah, if you sent me an email or turned in an assignment or something and I haven't graded it yet or got back to you, that's why. So don't feel like your email got lost. I'll take care of that, but I guess the good news with that is, now you have a little bit of extra time. So technically, you're supposed to watch the videos, not you guys that are here, but if you miss a class, you're supposed to watch the videos and answer the questions. But I haven't posted it yet for Friday. Anybody who was not here on Friday, I haven't posted it yet, therefore you're still okay. So I will hopefully post that today, and then you can watch those videos, answer those questions, and you will be counted as present. Or for the rest of you, if you were here on Friday, you can watch the video and get the points for everyone. Any questions about anything? Oh, all right, let's get moving then. So how many of you took biology because you didn't want to take chemistry? A few of you? Okay, well, the bad news is we're about to do chemistry, right? To truly understand biology, you actually do need to do chemistry. And that is what we are about to do. But actually, how many of you have had chemistry before? So this is an easy version of chemistry. It's one of those where there's no math involved. So here we go. Let's jump into it. Chapter 2, chemistry. Pull it up. Here we go. So at the beginning of the chapter always has a few pictures. I call it the guessing game. It's just kind of like, hey, why does this chapter matter to your everyday life, right? Because none of you are biology majors, none of you are chemistry majors, so why does it matter? And when we have time, I like to talk about it, and we do have time, so let's talk about it. First of all, can I tell me what this picture is? Can anyone guess? Yep, it is coral. Can you tell specifically what's going on with that piece of coral right there?
Isn't it hot losing its color?
Yeah, exactly. It's been bleached. Not literally, people didn't pour bleach into the water there. But what's happening is with warming climate and with an extra bit of carbon dioxide that mixes in the water that causes or creates a type of acid. And of course, that's bleaching these corals and it's dying. And it's a bad thing. So anyway, yeah, that's that. Any guesses to what this is? Fries, right? What's being poured on those fries? Yep, salt. And one of the reasons I love this chapter, and one of the reasons this chapter is so important, why chemistry matters, is because there's a lot of misinformation out there about chemistry. People try to scare you. You know, they'll give you some long chemical name or something, and like, oh, this is in your food, you don't want to eat it. But it's not necessarily scary. But let's talk about salt really quickly. We're going to talk about it a little bit later. But table salt right there. Does anybody know what it is? Like what the chemical is, what the compound is? Yep, sodium is part of it. Anybody know the other part? That's okay. If you don't, you will. It's sodium chloride. So the reason I find that interesting is because sodium is an explosive metal. So if you put sodium in water, it will explode. Chloride, the other part of it, chlorine, that's a poisonous gas, right? So what you're eating is an explosive metal and a poisonous gas. But the point is, obviously, when they're together, they're completely harmless. Well, not completely. It could raise your blood pressure if you have too much of it, but it's generally harmless, right? And it tastes good. But that's just a great example of how, when it comes to chemistry, right, people will try to scare you. They could try to scare you and say, you know, this thing is that, and this thing is that, but that doesn't matter. Like you get that with people talking about ingredients in vaccines. You know, that thing's really dangerous. Like, yeah, it is by itself, but when it's mixed with other things, not so much. Anyway, we'll talk a little bit more about that later. Anybody guess what this is? Yep, copper. I don't know why your book even included that, but I guess maybe it's just a metal that you guys all know, so they included it. But anyway, yep. So any questions about that? This is why chemistry matters. Obviously, you'll not get tested on any of that stuff. Your book also has like a theme for every chapter. So last chapter's theme was sea turtles. This chapter's theme is nuclear medicine, and we're going to skip that as we always do. But yeah, you don't need to know anything about radioactivity. It's in the book. But there it is. Could be good, could be bad. That's what your book is getting at, and you won't be tested on any of that. So let's just move forward. Here we go. This chapter is broken down into two main bullet points. Some basic chemistry is the first one, and then we're going to talk about water. So here we go. Like I said earlier, if you take to truly understand biology, you actually do need to understand chemistry, and that's what your book gets at. They say if you take apart any biological system, you're really going to look at the chemical level. So everything we learn, everything you're going to learn later, is all basically boiling down to chemistry. So we start there, right? We start with chemistry, and we start moving our way up. Here we go. Let's talk about some definitions that you need to know first. Does anybody know what the definition of matter is? I'm sure you guys do. You're probably just thinking, all right, do I want to say it? Am I going to say it the right way? Anybody want to take a guess what matter is?
Anything that occupies space is matter.
That's exactly what it is. It's exactly how your book defines it. And that is exactly what you need to know for the exam, and exactly what you need to understand. So when I use the word matter, you know what I'm talking about. Matter is anything that occupies space and has mass. We'll come back to that in a second. My next question will be, what is mass? But we'll talk about that in a second. The other thing we're going to talk about is the three states of matter. I'm sure you guys already know this, but what are the three states of matter? Yep, solid, liquid, gas. There's also other stuff, depending on what you read, but we're going to stick with your textbook. So yeah, solid, liquid, gas. You guys already know that. So let's talk about what mass is. Because if matter is anything that occupies space and has mass, then what is mass? Any guesses to what mass is? I like that. weight is a good example of mass, but really, it's the measure of the amount of material in an object, which again could be weight, right? I could put myself on a scale and say, I'm overweight, 240 pounds. Of course, you could also measure the amount of material in an object other ways, right? Like my drink out here has 28 fluid ounces, right? So I know how many fluid ounces that has. So yeah, matter is anything that occupies space and has mass. Mass is just the measure of stuff, right? Pretty simple stuff. Any questions so far? So I didn't make that name, I just found it and put it in there. Next word that you guys are probably already familiar with. Let's see if you can actually define it though. Element. How would you define that word? Like you all know what it is probably because you've grown up hearing it. But what is it? No guesses?
Book says it's a substance that cannot be broken down into other substances by chemical reaction.
Exactly. Can't be broken down into other substances by chemical reaction. So for example, glucose is not an element because it can be broken down, right? C6, H12, O6. So that means it's a bunch of carbons and hydrogens and oxygens. So you could use some chemistry and break it down into the carbons and hydrogens and oxygens. But that one carbon, for example, if we were to take one of those carbons, we cannot break that thing down anymore using chemical reactions. So the carbon is an element. If we were to take one of those oxygens from the glucose, couldn't break it down anymore with chemical reactions. Therefore, it is an element. And of course, this, I guess, is where the whole idea of radioactivity comes in. Even though I'm not going to test you on it, it is worth noting that you can break down elements, but not with chemical reactions. Those would be nuclear reactions. Right? So if you take uranium and split it, that would be a nuclear reaction. Any questions about what's on the slide? All right, it's a pretty easy step, right? This is probably a review for most of you. Your book points out that there are 92 naturally occurring elements. I'm not going to test you on that. That's not important for the grand scheme of the semester. That's
Can
right.
you go by like 3 seconds?
Go back.
Like 3 seconds.
Sure. And really, these words, for this slide, it's just important that you know what matter, mass, and elements are. It's important that you know that. No problem. Less so because I'm going to test you on it, because I probably won't test you on those words, but I'm going to use those words a lot this semester, so you need to understand what they mean when I use them. So like I said, your book points out that there are 92 naturally occurring elements. You do not need to know that number. This is also the examples that your book gave: carbon, oxygen, potassium, gold. You don't need to know those either. It's just examples. We're going to talk a lot about carbon and oxygen this semester, we think. So definitely this chapter, next chapter, chapter after that, yep. So carbon and oxygen, very important elements that we're going to talk a lot about. Anyway, your book also points out that these 92 naturally occurring elements each have their own symbol. It's derived from an English, Latin, or German name. You don't need to know that either for the exam, but your book included it, so did I, because it's a 100 level course and I teach out of the book. So any questions about this relatively unimportant slide? All right, so here are the 92 naturally occurring elements. Your book points out carbon as an example. You don't need to know that carbon's number is 6 and that its atomic mass is 12.01, but we will talk about it. I don't know, if anything, and you probably don't need to know this, but if anything, if I were to give you an element, a periodic table, and showed you carbon, for example, and then I said, what is the atomic symbol? Then if anything, you should be able to recognize, okay, if I give you this, say, yeah, that's the symbol, that's the mass, that's the number. If anything, but you probably won't need to do that either. So, any questions about this? Okay, well, we're moving right along. Here's a little guessing game. This is also really important, but people usually find carbon pretty boring, or excuse me, Chemistry pretty boring, so I'm trying to make it at least slightly interesting. Any guesses as to what that element is? There's two hints. One, you can see it, and that picture is a hint. No guesses? Does no one here like classic rock? I feel like that would be a good hint. It's Mercury, and apparently that's supposed to look like Freddie Mercury. Anyway, here's another dumb one. Any guesses as to what that is? Yeah, so that's copper. That should be a big one around here. A lot of people like to steal copper. These parts. How about this one? Not that you need to know this. No guesses? Get the lead out. It's lead, like Led Zeppelin. Man, I'm just old. All right, how about this one?
Iron.
Yeah, right, iron. Good. Anyway, fun's over. Let's get back into it. Your book also points out that there are 25 elements essential to humans. That is a number you do need to know. Now we're getting into some important stuff as far as the exam is concerned. You need to know that there are 25 elements essential to people. So if you were to look at your elements that make you up, there are 25 of them. Also, if you were to look at the elements that make you up, about 96% of what you are, of your weight, is made up of only 4 elements. So yeah, there's 25 of them, but then there's the big 4. That's what I call it. And you need to know the big 4. You take a note.
We should write this.
Yep. This is what you need to know. You need to know that the big 4 is oxygen, carbon, hydrogen, and nitrogen. I'm not going to ask you to memorize that percentage. Just know, for your own knowledge, that it's a large percentage, right? So most of you is made up of oxygen, carbon, hydrogen, nitrogen. You don't need to know them in that order. It's just randomly, that's how they are. The order doesn't matter. So if you were taking notes, if I were you, I would shorthand it, but big 4, and then like a colon, oxygen, carbon, hydrogen, nitrogen. Though it should be pretty easy for you to remember that because we're going to talk a lot about carbon, hydrogen, oxygen, nitrogen. So probably you won't even need to study to remember that. Those things are going to probably be burned into your brain because we're going to talk about them a lot. So anyway, yeah, again, you're made up of 25 elements. Very, 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 very large majority of those are the big 4, carbon, oxygen, hydrogen, nitrogen. But what about the other ones? Let's talk about the other ones here in a second. We'll talk about the other 4%, right? So if 96% of you is this, let's talk about the other 4. The other 4 is mostly made up of 7 other elements. The first one that we're going to talk about, in no particular order, is calcium. Does anybody know where you get calcium and why it's important? You probably do. You've grown up hearing this your whole life. Like, why do you need calcium? Why should you need calcium? Yes, sir.
Milk for bones.
Yep, milk. Yeah, you get it from milk, and it's good for your bones. That's exactly how I remembered it too. Yep, it's important for bones and teeth. And like he said, you can find it in milk or the other dairy products, yogurt, cheese, things like that. You can also get it in sardines, green, leafy vegetables. You do not need to know any of this. This is just an example. Your book is just giving you some examples of the other 4%, the 7 elements of the other 4%. Just an example. I'm not going to test you on this. This is not a nutrition class. The other one that you don't need to know for the exam, but let's talk about it anyway, is phosphorus. Anybody know why phosphorus is important or where you can get it? So calcium is good for your bones and teeth, and you get it from milk. I guess I'm asking a similar question about phosphorus. Why is it important, and where do you get it? That's okay. Here it is. Phosphorus is an important component of DNA. You'll see why later. It also makes up something called ATP, which you're probably going to be sick of once we get to that. We're going to talk a lot about ATP. So basically, without phosphorus, we definitely would not be alive. So what's important? Where can you find it? Eggs, beans, and nuts. Again, these are just examples. I'm not going to test you on it. This bullet point is incorrect because it says see the upcoming slides for the other 5. But I don't even talk about the other 5. You can look at them if you want. I'm not going to test you on them. just so far, what you need to know for the exam is the big four, right? The ones we talked about earlier, carbon, hydrogen, oxygen, nitrogen. You need to know what the big four are. But if you're interested in it for independent work, this is a good thing to write about if you want to. You could write about these 7 elements. Like, just like I have here, you could write about what they are, why they're important, where can you get them in your diet. Then there's this. Next thing you need to know, there's 14 trace elements. You don't even need to know that number. You don't need to know that there's 14 of them, and you don't need to know that specifically it's less than 0.01% of your body. The point is, I just want you to know that there are something called trace elements, and they make up a very, very, very small amount of what you are. But here's why it's interesting to me, because you need them, right? You need them, even though you only need a very small amount. And that's another thing you could write about for independent work. Essentially, everything is a poison. It's all about the dosage. So one of the things you could write about, pick any element and say, what dosage is that element poisonous? So you could ask, for example, what happens if you have too much iodine, or not enough iodine, or too much, I don't know, aluminum, or not enough aluminum, right? These things, that's a very important thing. And again, this goes back to the scare tactics people will try to use when they talk about chemistry. They can say, there's this element in that, this kind of element in that food that you're eating. And they're trying to scare you about it. Like, yeah, now you know, maybe it's a trace element. Maybe you actually need it. So anyway, one of the book examples is iodine. I'm not going to test you on this. It's just an example. But iodine deficiency causes something called a goiter, which is an enlarged thyroid. You can see right there. That's what that is. Where can you get iodine? You can find it in green vegetables, eggs, seafood, dairy products, and iodized salt. So when you hear or when you see something that says iodized salt, that's what it means. They literally added iodine to your salt because you need a little bit of it. But again, an idea for an independent work if you want, look it up. How much iodine is too much? There is such a thing as too much. Because again, essentially everything is a poison, depending on the dosage. Anyway, any questions about this? All right, I'll give you another example of a trace element, which again is poisonous if you have too much of it, but you need it in small amounts. Fluorine. That is added to dental products and drinking water and helps maintain healthy bones and teeth. My guy has very healthy bones and teeth, and he's happy about it. Also, just an example, I'm not going to test you on fluorine, but that is, again, a great example. And I have seen people fear-mongering with fluorine. They put fluorine in your water. It's poisonous. But yep, everything's a poison depending on the dosage. So yes, fluorine can be bad. And if you want to look it up for independent work, you can tell me exactly what dosage is bad and what happens if you have too much of it. Anyway, any questions about that example? All right, another good example is this, iron. Right, so when you see like on the cereal box or whatever, and it says iron, it is literally iron. It's the metal, right? So there is metal in your food, and you need it, right? We need iron for our blood, and it really is metal. If you click this, like if you download the PowerPoint, click this, should actually be 2 videos. It's great. It's 2 videos, and they both show the same thing, but it's people saying it different ways. So what happens is somebody is taking cereal that's fortified with iron, and they blend it up with some water, and then they put a magnet next to the blender, and you can literally see the iron, the metal, attached to the magnet. The only difference is one person trying to scare you with it, like there's metal shavings in your cereal. So they're doing it and they're trying to be scary about it. They're trying to scare you. And the other person's just like, the cereal is fortified with iron. I'm going to prove it to you. So again, people try to scare you. If people don't have a good understanding of chemistry, they can be scared. But yes, iron is another great example. We need iron, and it's in some of our food. Literally metal. We need metal. We need metal. Anyway, any questions about these examples? Again, it's just an example, so I'm not going to ask you about fluorine or iodine or iron. These are just examples. Here's a good visualization from your book. Again, Again, if anything for the exam, you just need to know the big four. Oxygen, hydrogen, nitrogen, carbon. You don't even need to know them in that order. You don't need to know that oxygen makes up 65% and hydrogen's 9.5% and nitrogen's 3.3%. You don't need to know any of that. Just, if anything, just know the big four. So, any questions about that? All right, let's move forward then. Here's some words you need to know. Let me ask you before I put the slide up. What happens if I put some things together? Like, let's say I put together one oxygen and two hydrogens, right? Make some water. What do you call that when you put things together? Not the action, not the verb of putting them together, but the noun. Like, what is it when you put some things together? Good, compound, and you do need to know that. Elements combine to form compounds. Compounds contain two or more elements in a fixed ratio. So the oxygen you were breathing is a compound. It's two oxygens, two oxygen molecules bonded together. Most of what you're breathing in is nitrogen, for example. You don't even know that, but it's like 80% of the air is nitrogen, also a compound. It's two nitrogens bonded together. The book gives you the example of table salt, which we've already talked about, and water. And again, like I said earlier, salt is such a great example because together, or excuse me, separately, those things are very bad, right? Sodium is explosive. Chlorine is a deadly gas. It was literally used in World War I to kill people. But you put them together. World War I, chlorine gas. Anyway, so does anybody have any questions about what compounds are? All right. The second word for attendance, if you're watching online, is phone charger. Thing that I apparently really need because I'm on red. Phone charger is the second word for attendance. So when you send me the email after class, that's the second word you're going to put in it. Anyway, any questions about what a compound is? Good. Let's talk about some other words. Probably words that you're familiar with already. This is probably going to be a review for you. But the next thing we're going to talk about are atoms. Each element, each of those 92 naturally occurring elements we talked about earlier, each one of the big four that we talked about, they all consist of one kind of atom. What is an atom? It is the smallest unit of matter that still retains the property of an element. You need to know that. So basically, it's as small as we can get and still be an element. So again, I used glucose as an example earlier. Glucose is not an element. It's a compound. It's made up of 6 carbons, 12 hydrogens, and 6 oxygens. And if you were to break that down chemically, that's what you would get, right? 6 carbons, 12 hydrogens, 6 oxygens. But those, let's talk about the carbon as an example, we cannot break that down using chemistry, right? Because if we do, it's no longer carbon. Because it is an atom. Any guesses to what that atom is on the screen? You don't have to know this. I'm just curious to see if anybody does know it. Sorry. It's helium. We'll talk about it here in a second. Any questions about this slide before I move forward so we can talk about the structure of an atom? Very good. Here we go. The structure of atoms. Very simple stuff. You probably already know this. Atoms are made up of subatomic particles. Protons, electrons, and neutrons. You need to know that. Those are the 3 things that make up an atom. Definitely need to know that. If you're interested, for independent work, you could look this up too, because protons and electrons and neutrons are also made up of other things that we don't even get into this class. But yeah, you need to know that atoms are made up of protons, neutrons, and electrons. You also need to know that protons are positively charged, electrons are negatively charged, and neutrons don't have a charge. You need to know that. Should be pretty easy to remember. Proton has a positive charge, so there's the P, right? That's easy to remember. Neutron, it's in the name, right? It's neutral. So I guess technically the hardest one to remember would be electron. But by process of elimination, hopefully you could easily remember that electron's a negative. Another way to remember that, if you will, getting electrocuted is a negative thing, right? It sucks to get electrocuted. Therefore, maybe that'll help you remember electrons are negative. This is actually really important. A little bit later in the semester, we're going to talk about some really important chemical reactions. And the fact that protons are positive and electrons are negative will come back into play. It's very important. Your book also points out that if the number of protons in an atom is equal to the number of electrons, then that thing is neutral. Which should make sense, right? If your negatives and your positives balance out, then you are neutral. And you need to know that for the exam, and you'll get really familiar with it in lab next week. But anyway, any questions about what's on this slide? Pretty simple stuff. You probably already know it. These are just some examples. Hydrogen and gold. You don't need to know those. They're just examples. Hydrogen has 1 proton and 1 electron. That thing's neutral. This gold, 79 protons, 79 electrons. It's neutral. Does anybody know what you call the inside of an atom? So if we're talking about the structure of atoms. We know they're made up of these 3 parts. What's the inside of an atom called? Does anybody know?
Nucleus.
Good, nucleus. Do you know what's in the nucleus? Good, protons is one of them. Protons and neutrons are in the nucleus. You need to know that. You need to know that the nucleus is on the inside. You need to know that it's protons and neutrons. Here's still something that we won't talk about, that you don't necessarily need to know for the exam, but it's good to know, I guess. It'll be slightly important later. Again, as a review, what charge do protons have? Positive, good. So here we are, we're looking at this uranium. So there's 92 protons right there, all squished together. Have any of you ever tried to put 2 magnets together that are the same, like a plus and a plus? What happens when you do that?
They don't stop very.
Yeah, like they repel each other, right? That's what happens here too. Protons repel other protons. Also electrons repel other electrons. So imagine how much energy it takes to squish those things together. They don't want to be together, but they are. They're compacted really tightly together. And just for your own knowledge, that's what makes nuclear explosions, for example, so powerful. Because all the energy that's holding those things together, when you break it, that energy is released. And that concept will be important later. The idea that electrons don't want to be next to each other and protons don't want to be next to each other, that's basically a big part of how chemical reactions work. You'll see why later. But anyway, the point I'm trying to make, the important thing that you're going to need to know later, however much energy it takes to build something, that's how much energy is there to be released when you break that thing. So if we're talking about molecules, like glucose, for example, all the energy it took to make that thing, that's how much energy will be released when you break that thing. Anyway, any questions about what a nucleus is? All right, so again, a nucleus consists of protons and neutrons. So then what's left? What's the other third one that we didn't say? What's on the outside of the nucleus? Electrons, good. You need to know that too. The nucleus is protons and neutrons, and the rest of it are electrons. Your book gives you an example of helium. So here, helium has 2 protons, 2 neutrons, 2 electrons. Just an example, I'm not going to test you on helium. But let's talk about some things you do need to know. For example, the atomic number. And again, we're going to use helium as an example. Atoms of an element have the same unique number of protons. So if you're taking notes, I'm trying to think of a good shorthand, you could put number of protons defines the element. Right? So again, using this example, helium has 2 protons. Everything that has 2 protons is helium. It is defined by that number. If you were to take a proton away from that thing and then only have 1 proton, that would be hydrogen. It would no longer be no longer be helium. Because again, it's defined by that number. If you were to add a proton there, so you have 3 instead of 2, it would no longer be helium. It would then be lithium. So again, basically what you need to know is that elements are defined by the number of protons. If you change the number of protons, you change the element. Any questions about that? All right. That brings us to the mass number. The mass number is the sum of the protons and neutrons. So again, using helium as an example, I already told you that its number is 2, meaning it's defined by the fact that it has 2 protons. That's what that is. And then this is the mass number, is 4, meaning it has 2 protons, 2 neutrons, 2 plus 2 equals 4. Then there's this weird number. We're going to talk about it in a second. The atomic mass is different than the mass number. Any questions so far? All right, and again, I'll remind you, the fact that we're talking about helium doesn't matter. Helium's not important. It's just an example. I'm not going to test you on that. And if I did, it wouldn't be about helium anyway, because as far as we're concerned, helium is a very unimportant element in biology. Anyway, if there's no questions, we will move forward and talk about that weird number at the bottom. Well, let me ask you this. The average human, how do I word this very correctly or carefully? Humans have an average of how many fingers? Any guesses there? What was the answer? Maybe be my guess. That makes sense, right? Look, everybody hold your hands up. As far as I can tell, I think everybody here has 10 fingers, right? So that's a normal answer, but that's not the correct answer. Think about it. Some people don't have all 10 fingers, right? And some people even have extra. So really, if you were to take an average and count every human's, everybody's hand that has hands, and then divide it by, 7.8 billion, how many people there are right now, the number probably wouldn't be 10. Definitely not exactly 10, right? Because the number varies. We don't all have 10 fingers. And that's where we get this weird number. The atomic mass is sort of like that. Let's talk about it. It's close to the mass number because remember, the mass number is the number of protons plus neutrons, right? So the helium's mass number was 4 because that's 2 protons and 2 neutrons. But what it is it's an average. So we'll use this as an example. Hydrogen. There's 3 different types of hydrogens. There's the one that we're pretty much familiar with that has 1 proton and that's it. That's the big one, right? That's the one we're really familiar with. Then there's the one that has a proton and a neutron. So its atomic mass is 2 because 1 plus 1 equals 2. Then there's the one that has 2 neutrons. So 1 plus 2 equals 3. So they have different masses. But if you were to take an average of them, actually, if you were to easily just take this average, 1 plus this one plus this one plus this one divided by 3, the average would be 2, right? You guys can see that, right? But the thing is, in nature, there's a lot of these and not many of these. So if you were to look at the atomic mass of hydrogen, and I'm going to go look it up here to be sure that I'm getting the right number, 1.008. This is really close to 1, right? So that tells you that most hydrogens are like that one on the left. Most of them only have the 1 proton, and they have that atomic mass of 1. But there are a few of those heavier ones, the H2 and the H3. Therefore, the atomic mass is 1.00. Not going to test you on that, but when you look at a periodic table now, you understand where that number comes from. And you can tell, sorry to go back here again, you can tell by looking at it what the number mostly is, right? So looking at nitrogen, it's 14.01. That tells me most of the nitrogens probably are 14. But there are obviously some small ones. Same thing with carbon, 12.01. That means most of them probably have the atomic mass of 12, but obviously somewhere in nature there's a small amount of heavier ones. Does that make sense? All right. Well, now that we've talked about it, I can tell you that for biology, that actually is not that important. So even if you don't understand it, don't feel bad because you can understand the rest of what I'm going to teach you this semester without understanding that concept. Anyway, are there any questions about that? All right. So again, I'll remind you what you do need to know for this exam is that an element is defined by its number of protons, right? So this thing, right, we're looking at 3 different things, but all of them are hydrogen because they all have that 1 proton. Because again, if you change the number of protons, you change the element. But what do you call it when you change the number of neutrons? And you do need to know this. Not the verb, But the noun, what is it called when you have the same element, but different number of neutrons? Any guesses? Actually, it's right up there. Yeah, the answer is isotope, and you do need to know that. Isotopes, they are the alternate mass forms of an element. And that'll be the next word for attendance if you're watching this online, isotope. So again, if you change the number of protons, you change the element. If you change the number of neutrons, what you have is an isotope. And that's, I guess the only reason that's even important is so you understand that word when I use it. So even if that's a concept you don't necessarily get, you might be okay for the semester. Because it's not that important for the biology that you will be learning. But anyway, that's the word, that's what it means. Yeah. And then your book gives us an example of carbon. Carbon 12, carbon 13, carbon 14. I'm sure you've heard of carbon dating. This is where that comes from. Your book talks about it. We won't. It's not important for the grand scheme of things. Anyway, any questions about what an isotope is? Again, this carbon thing is just an example. I'm not going to ask you anything about carbon 12, carbon 13, or carbon 14. Just an example. This next slide kind of goes back to what I was saying earlier. I was talking about the average human has how many fingers? That's what that is. Of course, I feel like that's probably a Photoshopped picture, but nonetheless, there are some people that have extra fingers, right? Also, some people have missing fingers. But again, just to reiterate what I was saying, carbon, like this carbon, for example, its atomic mass is 12 because it has 6 protons and 6 neutrons. 6 plus 6 is 12. This one's 13 because it has 6 protons and 7 neutrons. This one's number is 14 because it has 6 protons and 8 neutrons. But if you were to look at carbons in nature, most of them are this one right here. Not that you need to know that, but most of them are carbon 12, which is why the atomic mass is 12.011. It's also worth noting, too, again, that's an average. There is no one single carbon that has that mass, right? It can't be 12.011. It can't. It's just protons and neutrons. They all add up to 1, right? Those are whole numbers. So what we're saying is that's an average. Anyway, any questions about that? All right, your book also talks about radioactive isotopes. You don't really need to know that either. But a radioactive isotope is just an isotope where the nucleus decays, basically. So it's losing protons, losing neutrons, losing energy. And of course, that's where we get radiation from. Your book also points out there's some natural sources of radiation like radon, but you don't need to know any of that. So any questions about this slide? Moving right along. The next portion of this PowerPoint is called the process of science. And like I said last week, every chapter has this process of science thing. And it's good to read it. You should. It's good to think about those kind of things, but I'll never test you on it. So for that reason, I'm going to skip right past it. And actually, I think there are questions about this on the study guide, but it won't be on the exam. All right, let's talk about chemical bonding and molecules. Your book points out that it's only the electrons that are directly involved in a chemical reaction. Directly involved. I don't even know if I like that statement, but it comes from your book, so we'll stick with it. But it is important, and it does help you remember this other important concept, which is that the number of electrons determines the chemical properties of an element. So it's all about the electrons, for sure. So there's things called valence rings. This isn't even exactly 100% accurate either, but it's good enough for a 100 level class. But the first ring holds 2 electrons. The next ring holds 8 electrons. And that's as far as we get in this class. So technically, the larger ones that have more than those rings technically hold more electrons, but we don't worry about that. What you need to know for this course, so there's rings. The first ring holds 2 electrons. As far as you're concerned, everything else holds 8. So for example, again, looking at carbon back there, its number is 6. Therefore, you know, because its number is 6, that means it has 6 protons. And if I hadn't said anything about it being charged, meaning it's neutral, that means if it has 6 protons, it must have 6 electrons. Therefore, if I were to just give you that information and say, hey, carbon's atomic number is 6, you need to draw it because you wanted to do something like that. You should know, again, its atomic number is 6, therefore we know it has 6 protons. Again, because I didn't say anything about it being charged, we know that it must have 6 neutrons and also, excuse me, I don't want to confuse you. We don't know that. But we do know, because it has 6 protons and the thing's not charged, that we know it must have 6 electrons. Therefore, if you were to draw it, draw 6 protons, we'll just say 6 neutrons in the nucleus. How many electrons does the first ring hold? 2, right? So I could draw 2 little electrons. We know the other one holds 8, but we're not dealing with that many protons, right? Its number is 6. So we have 1, 2, 3, 4, 5, 6. Does that make sense? You should be able to do that. You'll do that in lab. You should be able to do that. If I give you the chemical number, if I give you the number, you should be able to draw it. Because you should know that the number, that equals the protons. If I don't say anything about it being charged, that also equals the electrons. And you know the first ring holds 2, and the outer ring holds 8. That's another concept. This outer ring, like I said, it holds 8. But how many electrons does carbon have on the outside? You can see it. Count it if you need to. 4, right? But I said it holds 8, but it only has 4. That, as far as we're concerned, is where chemical reactions come in. That thing holds 8. Not only can it hold 8, but it wants 8. It wants to be full. So it needs 4 more electrons to be full. Does that make sense? It only has 4. It can hold 8, so it needs 4 more. You good there? If we were doing oxygen instead, oxygen's number is 8. Right? So we know it has 8 protons. I didn't say anything about it being charged, therefore it must have 8 electrons. Right? So I draw the first 2, 1, 2, and then 3, 4, 5, 6, 7, 8. So now we have 1, 2, 3, 4, 5, 6 electrons on this outermost ring for oxygen. Make sense? Well, how many does it need to be full? If it has 6, how many more does it need?
2.
Good. And coincidentally, oxygen bonds twice because it needs 2 electrons. Carbon bonds 4 times because it needs 4 electrons. So as far as we're concerned in this class, that's the whole reason for chemical reactions. They're just trying to get a full outer ring, whatever it is they need to do to get a full outer ring. And that's what we call a chemical bond. There's also, to make it a little bit more complicated, 3 different types of chemical bonds, and you need to know each one of them. So we have ionic bonds, covalent bonds, and hydrogen bonds. You need to know those 3 different types. Does anybody know already what the difference is between them? Does anybody know which one is the strongest or which one's the weakest? You know that too. All right, let's talk about it. Let's talk about the ionic bonds. First of all, to remind you, like I said, if you change the number of protons, you change the element. Right? Carbon has 6 protons. If you take one away, you have boron. If you add one, you have nitrogen. Right? You cannot change the number of new protons without changing the element. Then, like I said, if you change the number of neutrons, you have an isotope. Right? So the only thing that's unaccounted for, as far as our discussion is concerned, is electrons. So what happens when you change the number of electrons? You get ions. And you do need to know that. So again, electrons are negative, protons are positive. So if you add electrons to something, it's going to become negative. If you take electrons away, it's going to become positive. And that's where we get ions. So again, if you change the number of protons, you change the element. If you change the number of neutrons, you have yourself an isotope. If you change the number of electrons, you have an ion. And because they are charged, right? Again, if you add add electrons, they become negative. If you take them away, they become positive. That's where we get ionic bonds and ionic compounds. It's because these elements are charged, right? Because they have extra electrons, or they have fewer electrons, whatever the case may be, they are charged. So any questions about what's on this slide? All right, there's one really, what's it, not popular. There's one ionic bond that's like probably in every single biology book, probably every single chemistry book. Just an example, but here it comes. We've already talked about it. Table salt, sodium chloride. So look, sodium, you can see here, has 1 electron on this outermost string, but it needs 8, right? So it's not even close to being full. Chlorine has 7, but it needs 8, right? So this thing has 1 too many, so to speak. This one has 1 too few, so they kind of team up, so to speak. Sodium's like here, you take the electron, right? And that is what we call an ionic bond. So when sodium gives up that electron, it becomes positive, right? Because now it has more protons than electrons, so it's positive. When chlorine takes that electron, it therefore is negative, right? Because the electrons are negative. And therefore, those things are attracted to each other. This thing has a +1 charge, that thing has a -1 charge, so they get together and kind of balance each other out. Does that make sense? That's how that works, and you need to know that. That is what an ionic bond is. You don't need to specifically know sodium chloride, that's just an example. You just need to know that that's how ionic bonds work. It's because they have charges, because there's too few or too many electrons. And because of that, they are charged, and because of that, they are attracted to each other. The last word for attendance, you're all 9. We'll stick with bonds. So James Bond is the last word, or words, if you will, for attendance. A proper noun, James Bond. Anyway, so any questions about ions? Download the PowerPoint, you can watch a little video of sodium giving up its electron, and chlorine taking it, and then getting together. And when we get back on Wednesday, we will talk about the other 2 bonds. So no questions? Yes?
Could you go back to baseline?
Yep. I'll go back, and the rest of you are free to go. That slide? Yes. Yeah, that'll be independent work, basically. Extra credit.
Awesome.
Yeah.
Awesome. All right, sir. Have a good
And
one.
then Wednesday, just come in on
Yeah,
Wednesday.
I'll be here.
Yeah. One. Tuesday, Thursday. Correct, yep. That's right, yep. Email it to you. Google Docs. So if you look